In the last video, we looked at molecular orbitals that were built from s orbitals. We got two of them, a sigma orbital for bonding and a sigma star orbital for anti-bonding. Now you can get the same kind of thing happening with p orbitals, but they have more complicated shapes than s's, so we get something new happening. Here is a p orbital on an atom. The nucleus of the atom is where that dot is. And here is a p orbital on another one. Now, you can get a sort of a head-to-tail interference on these. In the valence bond theory, we'd be looking for an intersection between those, and we'd call that a sigma bond because it lies along the bond axis, the imaginary line between these two nuclei. In the molecular orbital theory, we don't look at the overlap. We look at the interference of these things. If you drew the orbital that you would get, here are the two nuclei. What's happening is that these two electron clouds are interfering constructively, and they make an electron cloud there. So when you put a p here and a p here head to tail, you get this orbital. It's a sigma orbital, and it's made out of p orbitals. Let's say that these are 2p orbitals. I could call this a sigma 2p orbital. Now it won't be bonding because there are no nodes between these two. So you can get a sigma orbital from the p orbitals if they interfere head to tail. But what if you get them to interfere like this? Here's one of them, and here's the other one. What if they interfere side to side? You get these two lobes to melt together and these two to melt together, and your overall orbital looks like those two melted together on top and those two melted together on the bottom. Here are the two nuclei right there where those little dots are. Now what you get here is not a sigma orbital because notice that there is a node along the bond axis. So it doesn't touch the bond axis. Just like in valence bond theory, when we had an overlap that didn't touch the bond axis, when we have an orbital that doesn't touch the bond axis here, we call that a pi. And this is made out of 2p orbitals, so I can call this a pi 2p. So you can get sigma orbitals and pi orbitals. You can also get sigma star orbitals and pi star orbitals if they interfere destructively. Now, if they interfere destructively, you're going to get a node between the two nuclei. So here are the two nuclei, and if they interfere destructively, a node will be created. We saw how that happened in the last video when you had two S's coming together. They could interfere destructively if one was pointing up and one was pointing down. And it will turn out that what I will get is something like this. This will be a sigma star 2p orbital. Okay? And then how about this one? Can you get an antibonding for this? Yes, imagine that I put a node down the center of this, and the orbital has to shrink away from it. So here are the two nuclei. Here's the node. And I'm going to draw this, but I'm going to make this orbital shrink away from that. What I'm going to get is something that looks like now there's already a node here too, so there are two nodes here. This looks kind of like a d orbital, but it's not a d orbital because there are two nuclei in there. In a d orbital there will be one nucleus and it would be in the center, but here there are two. This would be a pi star 2p. It's an anti-bonding pi orbital. Alright, so how do these things fit into a molecular orbital diagram? Well, that's kind of complicated. And you'll have to be given the molecular orbital diagram whenever you've got things with two p's in there. Let me give you an example of one now. Here is the molecular orbital diagram for N2. It looks like this. You have a sigma from your 2s and a sigma star from your 2s. And then for your p, you've got two pi 2p's. Now, look at the pi 2p. We've got one in the plane of the paper. There'll be a second one between another pair of 2p's at right angles to this. And that's the other pi 2p. So there are two pi 2p's there. This is a sigma 2p. Up here is where the pi star 2p come in. And here is the sigma star 2p. Okay, so let's do the molecular orbital. Now this has to be given to you, and I'm not going to put a box around it. You don't have to remember this pattern. It'll be given to you on a test if I ask about this. Let's fill in the molecular orbital diagram for N2 and see what kind of bond order we get for it. Well, how many valence electrons do I have in each nitrogen? If you look at your periodic table the same way we always have, and if you look at where nitrogen is, you have 5 valence electrons for each nitrogen, so there are 10. So I'm going to fill in 10. 1, 2, 3, 4, 5, 6. Now notice I'm using Hund's rule. Remember Hund's rule said spread them out and line them up. So I'm going to spread them out first. 6, 7, 8, 9, 10. Alright, so let's figure out the bond order. How many bonding pairs do we have? Well, we have 1, 2, 3, 4 bonding pairs. How many anti-bonding pairs do we have? 1. So it predicts a bond order of 3 for this molecule. Is this molecule going to be paramagnetic or diamagnetic? Well, there's no unpaired electrons, so it'll be paramagnetic. Oh, it'll be diamagnetic, I'm sorry. Diamagnetic. And is it going to be stable? Well, yes, because there's the bond order is greater than 0. If the bond order is 0, it won't be stable. So it will be stable because I have a bond order of greater than 0. And there, I've described this pretty well. Now, if you look at the Lewis structure for this, it agrees with the molecular orbital theory's prediction that you should have a triple bond in here. Let's do another one. Let's do O2. The molecular orbital diagram for O2 is just a little tiny bit different. Here's your sigma 2s. Here's your sigma star 2s. Here's your sigma 2p. Here's your pi 2p. Notice that it's a different order than I had over here. Here's your pi star 2p. And here's your sigma star 2p. Let's fill in the molecular orbital diagram for O2. Okay, how many electrons? If I look at the valence electrons for oxygen on the periodic table, there are 6. So I'm going to have 12 electrons to fill in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now notice I used Hund's rule. I spread them out and line them up before I, as much as I can. Alright, so here is the molecular orbital diagram for O2. How about the bond order? Well, let me see how many bonding pairs. There's 1, 2, 3, 4. 4 bonding pairs. How many anti-bonding pairs? There's an anti-bonding pair here and a pair in an anti-bonding level, so I can say that that's an anti-bonding pair. So there's one there and one there, so there's 2. So I would expect there to be a bond order of 2. I would predict a double bond from molecular orbital theory between the 2 oxygens. And that kind of tallies with what the Lewis theory says. Here's the Lewis structure that we drew for the O2 molecule. It's got a double bond in it. So the molecular orbital theory and the Lewis theory agree that there's a double bond in there. How about the magnetic properties of this? Is it paramagnetic or is it diamagnetic? Now in this case you have unpaired spins, in fact 2 of them, and that means it's going to be paramagnetic. Now, when you have an unpaired spin, that's like a free radical. We said that those are very reactive. You have a diradical. You have 2 unpaired spins here. And this tends to make oxygen fairly reactive. In fact, oxygen supports combustion, which is a pretty violent reaction. Now, is it going to be stable, the O2 molecule? Yes, because we have a bond order greater than 0. All of your problems that you'll be asked to do on this worksheet and on the test will involve filling a molecular orbital diagram, predicting the bond order, predicting whether it's stable or not, and predicting what its magnetic properties are. If you can do those things, you should be able to complete the worksheet and the homework for Chapter 5.